Hi everyone, my name is Joe Crain and I'd like to recognize Nick Schulte who helped out on this presentation. Today I'm going to talk about paths towards implementing eDNA-based bioassessments across the United States. First, I wanted to do a super brief introduction of us as a company. We were founded in 2014 by myself and Noah Fear. And today we do a lot of aquatic environmental DNA for clients as well as animal diet. We process about 20,000 samples a year and have helped out over 400 clients. Since we started, we do a lot of next-gen sequencing, a lot of qPCR, and we're developing point-of-use tests. But mostly I'm going to talk about the aquatic environmental DNA side of things, some of our experiences in that, and working with different clients in the US. Now, in the US, we are required to quantify clean water in some fashion or another, and this is really revolving around the Clean Water Act that was founded in or passed in 1972, and that requires assessment of water quality, and for most states, that's biological assessment. We have a question when we start to take a look at this and all the data that have been collected is simply, can we map water quality across the US with how bioassessment is currently? And the answer to that is not really. The reason for that is a couple-fold. One of those things is that there's actually a little consistency among the US states in the taxa that are used for bioassessment, because the Clean Water Act is requiring individual states to meet the conditions of that act. Each one gets to set its own rules. And when we take a look at, for example, all the 50 states and which taxa they simply have chosen to use for biological assessment, some of those, like the great state of Virginia, only use macroinvertebrates. Others, for example, will use multiple macroinvertebrates and periphyton. Some will use fish as well as macroinvertebrates. And some, such as Washington State, for example, and Maryland, will use fish, amphibians, macroinvertebrates, and periphyton. So even at this point, when we're taking a look at comparing different states and water quality across those states, no less over time, you can see that currently there's different taxa that have been highlighted as being indicative of differences in water quality. In addition to different states using different taxa for water quality, there also haven't been consistent development or application of the different indices and models that are used to take those data on presence or relative abundance and turn that into indices of water quality. So here's another map, this one that Nick had put together, just looking at the different assessment methods and how those scores end up getting calculated. And you can see that some states will just use biotic indices, such as North and South Carolina over here. Others will use some type of multimetric index or index of biological integrity, and you can see a lot of states do that. Others will use observed over expected, and others still biological condition gradients. And we have this patchwork in the US where different states have made different choices. All of those have developed their own, and even states, for example, like in the Great Plains, that are all using some type of multimetric index. They've all been generated differently. They're all not necessarily intercomparable because they use different taxa, different scores associated with them. This patchwork is the reality of what we do in the US as far as bioassessment is concerned. In addition to not using the same taxa across different states and calculating scores differently, it turns out that when two states do use the same species, that often there's inconsistent tolerance values that are assigned to those species. So as an example, we took a look at fish tolerance values for the US and consulted 3 national databases and put together 15 state databases on tolerance values for fish. And across the US, there's approximately 1,355 different species of fish that are recognized by the different states. Half of those had tolerance values. 288 of those had differences in the values across the species. And even more extreme, 37 of those would have been considered tolerant in some places and intolerant of low water quality in other places. Just an example, fathead minnows in Maine are considered tolerant of low water quality. In Maryland, they're neutral, and in West Virginia, they're intolerant of low water quality. And these aren't differences in the biology of the species at different places, but more than likely, just differences in the expert opinion of whomever was putting together these databases. The sum of all this exploration, looking at how different states conduct their different indices, is that we really have a patchwork. And in order to unify it, it's going to take some work. So given that, how do we get to a consistent, comparable, robust approach to eDNA-based bioassessment in the US? Right now, we can already kind of do this. When we take a look at eDNA data that we've taken for different places like New Hampshire, Alaska, and Oklahoma, we can look at the fish species that were present in a particular sample, use average scores of tolerance values for the different species, and calculate water quality indices for each of these places using a unified approach. When we take a look at a subset of the data that we've collected across the US, this here is 100 different sites, using these average fish tolerance values over here, and just working off the species presence, you can see that our mean tolerance values for different sites range from relatively tolerant of low water quality all the way up to very intolerant of low water quality. And so we know that we can get a really broad gradient of water quality values using the data that we have, tolerance values that we currently have. The question that we have then are, what are the bottlenecks? If we want to do a national scale implementation of eDNA and get all the states on the same page, so we can start to take a look at water quality and start to compare that across sites, what are the bottlenecks? When we take a look at the entire process of generating eDNA-based bioassessment, there's really just a couple of things that we need to do. First thing we need to do is take a look at our primers. We need to test those out, decide which primers we're going to use for different taxonomic groups. We have to build reference databases, figure out how to do collections of water, and then take those back to the lab and analyze them. And then once we take those data, figure out how to generate these specific biotic indices. Individually, for bottlenecks, we're doing pretty well on primers. We still have a little bit of work to do, but we have our primers figured out. Reference databases, I'll talk about that in a little bit. Those are a big bottleneck for us. Going ahead and doing collections, we've got that figured out. Doing the lab analyses, we're good on that. Generating our biotic indices, still a bottleneck. Shouldn't necessarily be that difficult, but we haven't gone through all the steps that it's going to take the lab-based data and generate indices for it. When we take a look at the different groups that people use, so it's fish, invertebrates, and phytoplankton, and here we're just going to use diatoms as an example. In the US, we have for freshwater fish roughly 1,350 species. For invertebrates, it's roughly 3,000 species that get used for water quality, and this comes from USGS and EPA. And then for diatoms alone, ignoring the green algae, that's roughly 2,500 species that the USGS has data on. When we take a look at the reference databases that are out there, of the 1,300 roughly species of fish that we have in the US, only about a fourth of those have actually been sequenced and have full mitochondrial genomes. For inverts, it's even worse. There's only about 100 of those that exist out of the 3,000, and then about 10 diatoms out of the 2,500. So this is a huge bottleneck. We go ahead, we collect eDNA, we do the sequencing, we get lists of sequences back, and then we go to assign taxonomy, and we have a hard time doing that. And I know that we can do taxonomy-free assessments, but from an application standpoint, when we talk to people, we have to tell them what species that we actually found, give or take. And this gets really hard because we don't have those reference data. So thinking about implementation and what it's going to take to go ahead and really make this all happen, when we've taken a look at it and when we've talked to people, we think we'd have to have data for about 10,000 sites. That's a rough estimate. And again, we've been able to generate just on our own about 700 sites. That hasn't been too hard, but 10,000 is probably our magic number to really get a first good crack at this. It has to work across multiple stressor gradients, and we have to democratize that collection so lots of people can take it in the same consistent manner. 10,000 samples, it shouldn't be that hard to start generating indices that we can use across broad regions. And you can think of it in a couple of different ways. One is we start to take a look at all the data that we have for, say, fish, and then we might use some kind of multivariate statistic for that. Along one axis, we might say that, oh, it turns out that there's gradients in abundance of different fish species, and that might have to do with something like longitude. But then we take a look, and there's this other gradient that we find, and we say, oh, it turns out that that has to do with something like total phosphorus. And these total phosphorus gradients that we have right here could be one of our indices of water quality. And suddenly, just from having a large amount of data, then we can start to pull out the different gradients to which these assemblages are responding. Now, what we might be able to do is run the same types of analyses not only for fish, but also macroinvertebrates, phytoplankton, and you can imagine a situation where you were able to identify total phosphorus gradients across all of these sites for each of those different taxonomic groups. Once we did this, it would be relatively trivial to then generate nutrient indices, total phosphorus gradients, based on the relative abundance or abundance presence of fish, macroinvertebrates, and phytoplankton. Putting those all together would give us a multi-taxa view of what integrated phosphorus levels might be over time. When we look at how much an approach like this would cost to develop, we think it would cost less than $10 million, which is actually not that much money when you think about it. If we're going to do 10,000 sites and we want to get environmental parameters for those sites, such as nutrient availability, salinity, pH, turbidity, that rough estimate would be $500 a site. That's $5 million to do that. It's another $2 million to do the meta-barcoding, another $1 to $2 million to get reference databases for 6,000 taxa, and then working a little bit for methods and paying people salaries, and you're definitely under 10 million. So it's a reasonable amount of money to go ahead and do this. Money shouldn't be a bottleneck on this. It's not that expensive. Just one final thought. We're actually pretty close to being able to do a comprehensive eDNA approach to bioassessment across the United States. We just have to take care of a few bottlenecks, and we should be there. Happy to take any questions at this time.